Thanks for coming, everyone. As is pretty obvious, I've been working on creating 3D models out of rather large unstructured data sets. I've been doing my work at Curtin University over the university holidays. So the data sets that we're interested here are often very large and of interesting objects that sometimes we can't go back and revisit or are very expensive to go and revisit. And the other characteristic when we're looking at some of these data sets is they were taken years ago, maybe 5, 10 years ago, or that kind of span, where 3D reconstruction wasn't considered when they did it. However, with some advances in technology, we can look at that now. Some of the challenges that we've got with these data sets is, first of all, their size. So some of the exploration they did may have taken days or weeks, and so they've got a video archive or many hundreds or even thousands of photos of whatever it is they were looking at the time. Part of the issue with that is this heterogeneous acquisition where as they go around they sort of look at some things and then they come back to it later, they look at something else and sort of mix everything in together. And due to the age of these data sets and the way they've gone about doing it, sometimes they've got image quality and the cameras, or there's no details about where things are relative to one another. But ultimately what we want here is high quality, georeferenced, accurate, photorealistic, metric and complete 3D models. It's a tough ask and it's a bit of a mouthful, but hopefully we can get there. Now, the main data set that I've been working with is from the HMAS Sydney and the HSK Cormoran. Some of you may have heard of them. In 1941, both ships got into a bit of a fight with one another and they both sunk. They were only rediscovered in 2008 by the Finding Sydney Foundation, at which point they, over the course of about a week or two, took about 7 dives down to the ships and took a whole set of photos and videos. This whole dive was very, very exploratory in nature and trying to find out what happened. So the data set is not only large but unstructured and contains pretty much every challenge in the book. So when we're processing these data sets, we usually start with something along the lines of get all your images and find matching points between them. So when you do photogrammetry, you can, after you've got matching points, work out geometry from this. Unfortunately, this problem scales very, very poorly, as you can see here, and with 40,000 images, you're already looking at big problems. But the data set we have here is somewhat bigger. So over the course of these dives, they took almost 1,500 images, and then they took about 50 hours of video, which, if we looked at every single frame, is well over 40 million images, and this is a problem. There is some location data, but it's poor. They initially told me 13 metres accuracy. That's not quite right. It's often much, much worse. So unfortunately, that is useful in some ways, but not in others. So our normal procedure here of find matching points, all of a sudden you see it's going to be a very big problem. And then the other parts we go from there of determining the geometry and then texturing it all nicely. They would follow on nicely if we can do the first one. So from here, we made a few changes. And hopefully these changes do help a lot. So first of all, we need to extract all the frames from the video, but hopefully we need to do this in a smart way. After that, if we can classify the images and the video, we can hopefully make things neater and nicer and structure our data set a bit better. So first of all, as we're extracting frames from the video, because things are exploratory, it turns out that not every frame is useful. As I said before, they go around and they look at something for a while, and then all of a sudden they decide it's not interesting anymore and move on to something else. So if you start extracting every frame, you're just wasting a whole lot of data here, because you'll see like water for several minutes or longer. So as they're moving quickly, you want to extract more frames so you get everything that you can. As you're moving slowly, you want to do the opposite, take less frames, so you can minimise the amount of data that you actually have to process. After we have all of that data, we classify it and try and sort it into some sort of structure that we can then analyse in a quicker time than normal. So the location data, as I said before, doesn't exist for everything, but we can use it for some. So the other alternative then is to sort by what's in the images. We do this by basically selecting an image that contains a lot of detail and then matching this to other images to create a group of images, and then we, out of the ones that are left, we grab another image and continually sort them into groups that way. This is based on common image features, and then after that we can start matching images. So we then use all the data that we've collected so far. Time from the video, things that are near in time likely show the same thing. Things that are near in the location data that we do have, again, likely to show the same thing. And as I said before, the image classification already contains now some data that we can use there too. So this is some of the example data from the Sydney dataset. The top row there is from the still images that they took. This is just a sort of indicative sample of some of them. Some of them, as the one here you see on the far left, contain very little information. They've been so badly blurred and underexposed that there's not very much left, whereas the one on the right is pretty much perfect. It's crystal clear, good information, and all very nice. Likewise, the video at the bottom. As I said before, not every frame is useful. One on the far left, another good example. It's just water. The one on the far right, again, that's the best, probably one of the best frames I've seen out of the whole video. Whereas also you have the ones in the middle, so you've got motion blur and all sorts of other stuff in between. And this is the dive location data. Some of the more observant of you may have noticed, we have dives 1, 2, 3, 4, 6 and 7. 5 is conspicuously missing. And 1 is also deceptive. They've plotted the times when they didn't take the video footage. Not helpful. And also the scan patterns you see there, where it kind of goes side to side, that's not really accurate either. So the location data here is very approximate, but nonetheless it is helpful. So after throwing all of this stuff together, we do have some very useful 3D models. This one here is of the bow of the ship. This ship, as they got in the fight, got hit by a torpedo. So this mouse will work. Just about here is where the torpedo hit. And this snapped off as the ship sunk. However, this rather large chunk that's out of here is shown very, very briefly, very badly in the video, and hence isn't reconstructed as a 3D model. One of the other rather nice models that we got out of this was the foredeck of the Cormoran. My understanding is this is the first model that's ever been made of the Cormoran, and it actually came out surprisingly well and surprisingly quickly. So, just a bit of annotation here. This is the anchor on the very front of the ship. So this here is the front of the bow, and then this is one of the guns here on the side. So this is just both sides of the ship. So in conclusion, the methods that we've developed here show great potential for analysing these types of data sets. The HSK Cormoran and the Sydney is only one example of this. Hopefully in the next coming weeks or months we can analyse some other data sets and do some more proof of work on this. So in general, when you're looking at these data sets, if you're aiming to collect them in the future, more data is better. You can always throw it away, but it's very, very hard to get it back if you never collected it in the first place. Likewise, data quality is one of those things that is the same as more data is better. Do it well, do it right, and then you can use it very easily. So from here, there is some more work that we aim to do. Refining the location data, maybe using a combination of the location data and the video, and then work on some more large-scale reconstruction using some more robust algorithms. That's it. Thank you.
Thanks for the presentation. Are there any questions?
How long would it take to make up those 3 models?
It depends a lot on the sort of the structure of your data, if you have it, and also the quality of the images. Smaller images you can process quicker because it's just less data. Bigger images take longer. So let's see, this one here of the Cormoran I think was about 2,000 images. That's just of that part of the ship. The whole data set that I processed for that was I think about 25,000. That took I think 2 days. on my PC after running the whole stuff. And then just to texture it took, I think, 8 hours.
Offshore industry. There's for many years as-built surveys of long pipelines, jacket structures, or subsea structures which contain billions of hours of video at very high resolution, a lot of spoons. Did you give any consideration for approaching the offshore industry to see whether you could do this sort of application for, say your Franklin jacket installations or quality control and inspection? Because there'll be a lot of ROV injury and still photography associated with that.
Yeah, I think we briefly talked about it at one point, but we haven't done anything about it, no.
In general, it's possible. So the problem I think you will face, they look quite similar over a long distance. So this matching process will be a problem, but if you have a good parameter of the experimentation, you maybe could overcome this problem quite easily.
Actually, on that same line, do you think you would also be able to look at non-living structures like cement groundwater, would technique work with something that's more natural?
My understanding is it should, partly because of the results I've seen out of this. As some of it is seabed stuff, it has created flat pieces of seabed for me. While not very interesting for this, it's, yes, should do, should work. Again, it's a case of exterior orientation is good because the seabed looks very, very similar over large things. And being flat, it's one of those things that can warp. So if you've got some good at data from IMU or something similar, you should be able to sort that out relatively easily, I think.
So basically you need an image of the same surface on 2 shots from 2 different positions. That's required.
That's correct.